Hello and welcome to Engineerism. In this video, I'll talk about numbering and coding systems. And this video will be useful if you are preparing for the FEOP exam. So, first of all, let's talk about binary systems. So we know computers, they use zeros and ones to process any information. And this is called binary because basically it's either 0 or 1, so it's 2. And also we refer to it as base 2. So if you're given a number, it will be base 2 basically. So zeros and ones are used because they represent the two voltage levels. Of on and off kind of states. Zeros or 0 and 1 or zeros and ones are called bits. So now I'm going to go through an example. Let's convert 35. So actually, let's convert. We have a decimal number, and we want to convert it to binary. So let's see how we can convert a decimal to binary. So decimal means it's a base 10. Binary means it's base 2. Base 2 means either 0 or 1. So let's start with an example. 35 decimal base 10. We want to find the equivalent in base 2. How do we do that? So basically you take the decimal number and you divide it by the base you want to convert to. So 35 divided by 2 is 17 with a remainder, so R stands for remainder of 1. So this position here is the least significant bit, and that's important. We'll see why. So then what you do, you take 17 divided by 2, which is 8. So I have a remainder of 1. Then you take 8 divided by 2, which is 4. The remainder is 0. Then you take 4 divided by 2, which is 2, with a remainder of 0. 2, you bring this 2 here. 2 divided by 2 is 1. The remainder is 0. Then 1 divided by 2 is 0. The remainder is 1. And you stop. This is the most significant bit position. Then how do you write this number? You start from the most significant bit to the least significant bit position. So in my example, basically I'm going to write 1 first, 0, 0, 0, 1, 1. So 35 in base 10 is the equivalent of 1, 0, 0, 0, 1, 1, base 2. because this here is the most significant position, and this one here is the least significant position. So if I want to go back from binary to, and we have examples to do that. I guess I'll wait until I do that example. So now let's convert binary to decimal. So binary means base 2, decimal means base 10. And here's the number. And we just did this, so this better be 35. So how do you figure this out? You basically start from here, the back, so that you take 1 times 2 to the power of 0. So basically this is here, position 0, 1, 2, 3, 4, 5. So this one here, you just brought it here. Since I'm dealing with base 2, so tier 2 to the power of 0, because it's position 0, plus 1 times 2 to the power of 1, plus 0 times 2 to the power of 2, plus 0 times 2 to the power of 3, plus 0 times 2 to the power of 4, plus 1 times 2 to the power of 5. 1 times 2 to the power of 2 to the power of 0 is just 1, plus 1 times 2 is just 2, plus 0 times anything is 0, plus 0, plus 0, plus 1 times 2 to the power of 5, that's just 32. 32 plus 2 is 35, plus 34 plus 1 is 35. Paste in. So that checks. Now let's convert another binary to a decimal. So we have 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1. So this is base 2. So again, this is position 0, position 1, 2, 3, 4, 5. So again, you take these as, so 1 times 2 to the power of, basically you bring 0 here, plus 0 times 2 to the power of 1, plus 1 times 2 to the power of 2, plus, you bring 0 here, 0 times 2 to the power of 3, plus 1 times 2 to the power of 4, plus 1 times 2 to the power of 5. 1 times 2 to the power of 5 is 32, plus 1 to the power of 4 is 16. 0, this is just 0, plus 1 to the times 2 to the power of 2 is 4, plus 0 times 2 is 0, plus 1 times 2 to the power of 0 is just 1. So 32 plus 16, that's 48, plus 4 is 52, plus 1 is 53 base 10. So that's one way so this is one way to come up with this calculation. So now let's convert decimal to binary. So we have 40 base 10. We want to find what is the equivalent in base 2. So again, the same kind of concept. 40 divided by 2 is 20. So remainder is 1. So again, this is the least significant bit. Then you take 20 divided by 2 is 10. So 0. 10 divided by 2 is 5. The remainder is 0. 5 divided by 2 is 2. The remainder is 1. 2 divided by 2 is 1. The remainder is 0. Then you take this 1 divided by 2 is 0. And the remainder is 1. This is the most significant bit. And the way you write this is from the most significant bit to the least significant bit. That means 1, 0, 1. So 1, 0, 1. It gets kind of messy. 0, 0, 1. Base 2. Oh, sorry, this should be 0 here, because 40 divided by 2 is 20, so that's the remainder is 0. That means this here would be 0. Sorry about that. So now let's convert 63 base 10 to base 2. Kind of the same concept. So you take 63 divided by 2 is 31. The remainder is 1. So we just need to remember this is the least significant bit. Then 31 divided by 2 is 15. Remainder 1. 15 divided by 2 is 7. Remainder 1. 7 divided by 2 is 3. Remainder 1. 3 divided by 2 is 1 with a remainder of 1. And 1 divided by 2 is 0 with a remainder of 1. This is the most significant bit. And the way we write it, most significant bit to least significant bit. That means we start with this one here. 1, so you have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Base 2. So that's how you convert from one base to another. And basically that's how the computer works, because to the computer 63, it has to be in the equivalent of zeros and ones. Thank you and have a great day.